Hello friends, welcome to online lecture series. Today we will just see the another application of differentiable equation, and today we will just cover the next topic. The topic is heat flow. So we already know how the heat is flowing. The heat is flowing from higher temperature to lower temperature. According to that, we have to find the temperature which is flowing from your higher to lower. For that, we have to use the Fourier law of heat conduction. So let's start the topic, heat flow. The statement of the heat flow is given by the Fourier. He said that the heat flux Q, the Q is a heat flux through an area element A is proportional to temperature gradient normal to the area. In another way, we say that the rate of heat conduction per unit area is directly proportional to the temperature gradient. So according to your Fourier, we said that any particular heat which is flowing, any material, its rate of heat conduction per unit area is directly proportional to the temperature gradient. And this can be defined with the help of this particular formula, and this is defined by Q equal to the thermal conductivity into the area of that material from which we are passing the heat. And lastly, the temperature gradient. Temperature gradient means the rate of change of your temperature at a distance, which is defined by the equation Q is directly proportional to the A times dt upon dx. This equally proportional is defined with the equal sign by multiplying your right hand side by minus k, where k is called as constant of proportionality, or is said to be the thermal conductivity. So according to the Fourier, the heat is flowing from your higher to lower. Then the value of your this k is suppose higher, then the good heat conductor we are used. If the value of your k is so small or very small, then the conduction of your heat is very poor. So we will see some notes here. The minus sign is attached because the Q is positive as your temperature or the distance is goes on increasing. The heat flow from your hot to low is given by the negative sign, and the dt upon dx is negative. For that, we have to mention the negative sign. What particular materials are used for conduction of your heat? If we use the hollow pipe, then the A is nothing but 2 pi x. If we use a spherical shell or the spherical shell type materials, then A, that is the area, is 4 times pi x square. So in this way, we can find the conduction of your heat in that material. Some basic terminologies we have to use here. Suppose this is a simple figure is shown. The figure is the hollow pipe cross section. When we just take the cross section of the hollow pipe, we just get such type of figure. This figure have two particular diameters. One is inner diameter, which is denoted by D. With the help of your inner diameter, we can find the inner radius, that is a D upon 2. The blue shaded portion is nothing but the outer covering or the thickness of that particular material, and that thickness value is supposed dx. We have to find the outer diameter. The outer diameter can be found by adding the 2 times thickness on your inner diameter. We got the outer diameter, and half of your outer diameter is nothing but the outer radius. So we have two particular distance. In this white portion, the temperature of that particular material is very high as compared to the outer surface. So when we go from your origin towards the outer diameter's end, the temperature of that particular heat is reduced, and we have to find the temperature of that particular heat at any particular distance with the help of the differentiable equation. And that differentiable equation is your Q is equal to minus Ka dt upon dx, where x is nothing but the distance where we have in this particular figure. We will see one small example to understand our concept. The example is here. Example is here. A steam pipe 20 meter in diameter, which is protected with 6 centimeter thick, for which the coefficient of thermal conductivity is K equal to 0.0003 calories per centimeter in steady state. Find the heat loss per hour through a meter length of the pipe if for inner surface of the pipe is at 200 degrees Celsius and the outer surface is 300 degrees Celsius. Means we have to find how much heat is flowing in this particular pipe. The pipe is containing steam which has 20 centimeter diameter. So we have to just mention all the given fields. For that, we draw this diagram. Then the value for K is given by 0.0003 calories per centimeter. The inner diameter is 20 centimeter. Half of it becomes the inner radius. And this 30 centimeter is the outer temperature, which is outside this protection. Then we have to find the outer radius. For that, we require the thickness. The 6 centimeter thick outer covering is for that pipe. So the outer diameter becomes d plus 2 times dx. Value for d is 20 and value for dx is 6. 6 into 2 becomes 12. 12 plus 20 becomes 32 centimeters. And the inner diameter, we already find it. We have to find the outer radius, that is nothing but 16 centimeters. We have to find the value for Q. And here the hollow pipe is defined. So the value of your A is the area of that particular pipe is 2 pi x. For that, we have to use the Fourier law of heat conduction, and is defined by K minus K A dt upon dx is equal to Q, or we say that Q is equal to minus Ka dt upon dx. But we know that the value for A is here 2 pi x. So we have to replace the value for Q. There is a 2 pi x. So we got Q is equal to minus 2 pi xk dt upon dx. This differentiable equation contains two variables. One is temperature, one is distance. So we have to convert this differentiable equation into variable separable form. For that, we have to convert this differentiable equation into variable separable form. The q times dx upon x is equal to minus 2 pi k dt. So we have two particular conditions. At the inner surface is 20 degree Celsius. The distance is your inner radius, and your outer surface is contains 30 degree Celsius temperature, and we know the outer radius of this particular hollow pipe is 16 centimeter. So we got two conditions. So at t equal to, means at x equal to 10 centimeter, there is inner radius. The temperature is 200 degrees Celsius. For the 16, it is 30 degrees Celsius. So we have to just find the integration of this variable separable form, just putting the upper and lower limit. At x equal to 10 and 200, and your t runs from, x runs from 10 to 16 and t runs from 200 to 30. So we have to replace the limit of that variable. And we know that the integration of your dx upon x is log x. Before that, we have to just take the constant terms outside your integration. The q is a constant in my first integration, and second, the minus 2 pi k is again constant in my second integration. But taking outside the integration, common field outside the integration, we get q integration dx upon x is equal to minus 2 pi k integration of your dt with their limit. So integration of your dx upon x is your log x, and the upper limit is 16, lower limit is 10. And your right hand side integration of your dt is your t, whose limit is from 30 to 200. So upper limit minus lower limit, we got q into log 16 minus log 10 is equal to this minus 2 pi k 30 minus 200. After making the subtraction on your right hand side, we got minus 2 pi k minus 170. And on the left hand side, the log a minus log b, log 16 upon 10. So log 16 upon 10 is log 1.6, and the right hand side, that is a 2 into 170 becomes 340 pi k. And we know that the value for pi is 3.14. The value for k is 0.003, and value of your log of 1.6. When we use the calculator to find the value of your log, we have to use the ln. So the value of your log 1.6 is putted, and making the final calculation on your calculator, we got the value for q is 0.68144,15466 calories per second. This is the value of your q. Value of your q. They ask, we have to find the value heat conduction or the heat loss per hour through a meter pipe. For that, we have to multiply this q by 100 into 60 into 60. When we multiply this q into 100 into 60 into 60, we get a final solution of the heat flow. That is a 245318.9668 calories. This is the conduction of your heat, which is flowing in a meter long pipe. This is calories per hour per meter. In similar way, we can find the temperature at any distance in this particular heat flow. For that, we will see the second example. A pipe 20 centimeter in diameter contains the steam at 150 degrees Celsius, is protected with a covering of 5 centimeter thick of for which K equal to 0.0025, if the temperature of the outer surface of the covering is 40 degrees Celsius, find the temperature halfway through the covering under the steady state condition. Means we have to find the temperature of that particular heat halfway through the covering. For that, we have to just find the inner diameter, outer diameter. For that, we are defining this particular diagram. In this example, the value for K is equal to 0.025 is here. The inner diameter is 20 centimeter. From that, we can find the inner radius 10 centimeter. The outer diameter of our surface, which is 30 centimeter. When we find the inner radius is 10 centimeter and the outer radius is 15 centimeter, so in this particular figure, we observe that the inner surface is protected, inner surface containing the steam which temperature is 150 degrees Celsius and outer surface temperature is 40 degrees Celsius. So again, we have to use the Fourier conduction heat formula, and halfway through the covering, we will see later on this what is how to find this. So the covering of this particular pipe is 5 centimeter thick, and the inner radius is your X, and we have to just find the temperature of this particular pipe, which is half to the covering. Is the half covering, what temperature is there? For that, we have to just do this particular X plus dx upon 2 is the distance from your origin to the half covering of the surface. So heat conduction for again the pipe, the value for A is equal to 2 pi x. We got this particular table, the value at x equal to 10, the T is equal to 150, x equal to 15, T is equal to 40, x equal to 12.5. What will be the temperature at that distance? So by the Fourier law of heat conduction, the value for Q is equal to minus K Ax dt upon dx. Again, the A is equal to 2 pi x. We have to replace the value of A, that is a 2 pi x. Again, we have to convert the variable separable form of this equation. The variable separable form is why variable separable is here. And we have to use the first two conditions on this variable separable form. Means at x equal to 10, T equal to 150, x equal to 15, T is equal to 40. So taking the integration with limit 10 to 15, 150 to 40. So this is the limit of your integration of your distance, and the right hand side is the limit of your integration with temperature. Again, we know that the integration of your dx upon x is log x, and the right hand side, the integration of your dt is equal to t. Before that, we are taking the common q and minus 2 pi k. Then integration log x, putting your upper lower limit, log of 15 minus log of 10. Again, we have to make the subtraction. Again, log a minus log b is log a upon b. Q into log 15 upon 10 is equal to minus 2 pi k, and the subtraction of your 40 minus 150 is 110. So we got the value of your Q. The value of your Q is 220 pi k upon 1.5. So we have to find the temperature of at 12.5 distance. For that, we have to use the condition number first and the condition number third. At x equal to 10, the temperature is 150. 12.5, what will be the temperature? Again, we have to use the Fourier law. Again, the variable separable form, we are putting the limit reduced form 10 to 12.5 and 150 to the temperature which is unknown. We have to find at distance 12.5 what is the temperature. So again, taking the q and minus 2k pi constant outside your integration, taking the integration of this particular differential equation, representation of your 1 upon x dx is log of x. Upper and lower limit replacement, we got log of 12.5 minus log 10 minus 2k pi t minus 50 150. K get cancel, again pi get cancel, and the 220 is divided by this 2, we get this 110 log 1.25 divided by log 1.5 is equal to minus t plus 150. The minus this sign multiply to the inside this bracket, we get minus t plus 150. Again, we have to just put the value of your log 1.25 and log 1.5. We got the final answer of this left hand side is 60.5373 is equal to minus t plus 150. After solving this, we get the value for t is equal to 150 minus 60 minus 53. So value for t is equal to 89.46. So at the distance 12.5, the temperature is 89.46. In this way, we can find the temperature at any distance from the origin to that material. Thank you. We will see next topic on your next lecture.